Welcome to the cosmos where even the smartest AI can't fully explain these 10 mind-bending mysteries. I'm Dencio Anso, and today we embark on a journey to the very edge of human and artificial understanding. We live in an age of unprecedented technological advancement, where artificial intelligence can compose symphonies, defeat grandmasters at chess, and even design new molecules. Yet, when we turn our gaze, and our algorithms, to the vast expanse of the universe, we find ourselves humbled. The universe, in its infinite grandeur and complexity, still holds secrets that elude even the most sophisticated computational minds. These aren't just small gaps in our knowledge, they are profound chasms, challenging the very foundations of our reality. Think about it. We've built machines that can learn, adapt, and predict with astonishing accuracy. We feed them colossal datasets, hoping they'll discern patterns that our own brains, forged by eons of evolution, might miss. And in many fields they do. But the cosmos plays by a different set of rules, or perhaps rules so deeply encoded that even our most powerful AI tools are still like infants trying to decipher an ancient cosmic manuscript. The questions we're about to explore are not for lack of trying. They represent the current frontier where human ingenuity and artificial intelligence alike stand, staring into the profound unknown, sometimes with more questions than answers. So, prepare yourselves. We're not just listing facts here, we're peering into the very nature of existence, time, and space. We'll explore phenomena that defy easy explanation, that push the boundaries of physics, and that make us question what we think we know. From the invisible scaffolding of the universe to the very fabric of reality itself, these are the enigmas that keep cosmologists, physicists, and yes, even AI developers up at night. Join me as we delve into 10 cosmic conundrums that our silicon counterparts are still scratching their virtual heads over, reminding us that the greatest adventure is the quest for knowledge itself. First on our list is the universe's dominant, yet unseen, resident dark matter. Imagine, if you will, that everything we can see, the stars, the galaxies, the planets, you and I, accounts for a mere 15% of all the matter in the cosmos. The other 85%, that's dark matter. It doesn't shine, it doesn't reflect light, it doesn't interact with ordinary matter in any way we can easily detect, except through its immense gravitational influence. It's the invisible puppeteer, pulling the strings that hold galaxies together, preventing them from flying apart as they spin at incredible speeds. Without dark matter, the cosmic structures we observe simply wouldn't exist. Our own Milky Way would be a diffuse cloud of gas and stars, unformed and chaotic. It's the unsung hero, the cosmic scaffolding upon which the universe as we know it is built, yet it remains stubbornly, tantalizingly out of sight. Scientists, armed with sophisticated detectors buried deep underground or orbiting high above Earth's atmosphere, are on a relentless hunt for this elusive substance. We've theorized various candidate particles, WIMPs, axions, sterile neutrinos, but so far, direct detection has proven to be an incredibly challenging endeavor. Even our most advanced AI algorithms, sifting through mountains of data from particle colliders and astronomical surveys, struggle to pinpoint its true nature. They can model its gravitational effects with precision, mapping its distribution throughout the cosmos, but the fundamental question of what is it remains unanswered. It's like knowing a ghost haunts your house because the furniture moves, but you can never quite see the ghost itself, a profound mystery at the heart of cosmic composition. If dark matter is the universe's invisible anchor, then dark energy is its mysterious accelerator. For decades, we thought the expansion of the universe initiated by the Big Bang would be slowing down due to the mutual gravitational attraction of all the matter within it. Imagine throwing a ball upwards. You expect gravity to eventually slow it down and pull it back. But in the late 1990s, astronomers discovered something truly astonishing. The expansion of the universe isn't slowing down at all. In fact, it's speeding up. Galaxies are flying away from each other at an ever-increasing rate, propelled by a force we can't see, can't explain, and can't directly detect. We call this force dark energy, and it makes up roughly 68% of the total energy density of the universe. This is more than just a puzzle. It's a fundamental challenge to our understanding of cosmology. What is the nature of this pervasive energy that seems to be embedded in the very fabric of space itself, causing it to stretch and expand faster and faster? Is it a cosmological constant, An intrinsic property of space, as Einstein once proposed and then famously retracted, calling it his biggest blunder? Or is it something even more exotic, a dynamic field that changes over time? AI models can incorporate dark energy into cosmological simulations to match observations of distant supernovae and the cosmic microwave background, but they cannot tell us it exists or it is. The universe is not only expanding, but it's accelerating into an unknown future, driven by a force that remains a complete and utter mystery. When we gaze up at the night sky, we see a seemingly endless expanse. But what is the actual overall shape of the entire universe? Is it flat, like an infinite sheet of paper extending forever in all directions? Or is it curved, perhaps like the surface of a giant sphere, meaning if you traveled in a straight line long enough, you'd eventually return to your starting point? Or could it be negatively curved, like a saddle, also extending infinitely but with a different geometry? These aren't just abstract geometric musings. The shape of the universe is intimately tied to its density and its ultimate fate. The geometry of the cosmos remains one of the biggest outstanding questions in astrophysics, a grand cartographic challenge. Our current best measurements, primarily from the cosmic microwave background radiation, the afterglow of the Big Bang, suggest that the universe is remarkably flat, or very close to it, on the largest observable scales. This flatness presents its own set of puzzles, often addressed by the theory of cosmic inflation. However, very close to flat still leaves room for subtle curvatures that could have profound implications. AI can help analyze the incredibly complex data from telescopes like the Planck satellite, searching for tiny anisotropies that might betray the universe's true form. But distinguishing between a perfectly flat universe and one that is so unimaginably vast that its curvature is imperceptible to us is an immense challenge. We are, in essence, cosmic surveyors trying to map a territory whose boundaries, if they exist, lie far beyond our current observational horizon. Consider the curious case of time. We experience it as a relentless, unidirectional flow, an arrow always pointing from the past, through the present, and into the future. Broken eggs don't unscramble, spilled milk doesn't gather itself back into the glass, and we all age, never growing younger. This arrow of time is a fundamental feature of our reality, deeply embedded in the second law of thermodynamics, which states that entropy, or disorder, in an isolated system, tends to increase over time. But here's the rub. The fundamental laws of physics that govern the behavior of individual particles, like Newton's laws or the equations of quantum mechanics, are largely time-symmetric. They work just as well forwards as they do backwards. So why is the macroscopic world so different? This asymmetry, the stark contrast between the reversibility of microscopic laws and the irreversibility of macroscopic phenomena, is a profound puzzle. AI can simulate complex systems and even model scenarios where time might appear to loop or reverse under specific, controlled conditions, especially in the quantum realm. However, applying these models to explain the consistent, everyday experience of time's forward march for the entire universe is another matter entirely. Why did the universe start in a state of such low entropy, allowing for the subsequent increase that defines time's arrow? Is the arrow of time an emergent property, a statistical inevitability, or is there something deeper about the nature of time itself that we're missing? Even the smartest algorithms can't untangle this temporal knot. Black holes, regions of space-time where gravity is so overwhelmingly strong that nothing, not even light, can escape their grasp. They are the ultimate cosmic vacuum cleaners, swallowing matter and energy with impunity. For a long time, the classical understanding was that whatever falls into a black hole is lost forever, its information content effectively erased from the universe. This, however, creates a serious problem when you consider quantum mechanics, a cornerstone of modern physics which insists that information can never truly be destroyed. This clash between general relativity, which describes black holes, and quantum mechanics leads to the infamous black hole information paradox. Does a black hole truly obliterate information, or is it somehow preserved and eventually released? Stephen Hawking proposed that black holes aren't entirely black. They slowly evaporate over eons by emitting what's now known as Hawking radiation. But his initial calculations suggested this radiation was thermal, meaning it carried no information about what fell in. This intensified the paradox. Physicists have proposed various resolutions, from information being encoded on the event horizon, the holographic principle, to it escaping through subtle quantum effects during the final stages of evaporation, or even tiny baby universes budding off. AI can simulate the extreme conditions near black holes and model quantum behavior, but reconciling these two fundamental theories of the universe in this context is a monumental task. The debate rages on, and the fate of information in these cosmic abysses remains one of physics' most baffling enigmas. Prepare for a journey into the truly bizarre realm of quantum mechanics, with a phenomenon Albert Einstein famously called spooky action, at a distance quantum entanglement. Imagine you have two particles, linked in a special way. Once entangled, these particles remain connected, no matter how far apart they are separated, whether it's across a laboratory bench or across opposite ends of the galaxy. If you measure a property of one particle, say its spin, you instantaneously know the corresponding property of its entangled partner, as if they are communicating faster than the speed of light. This isn't just theory, it's been experimentally verified countless times, shaking our classical understanding of space, time, and causality to its very core. How can two particles influence each other instantly across vast distances, seemingly violating the cosmic speed limit set by light? This is where our intuition and even our most sophisticated AI models begin to falter. AI can certainly be used to design and analyze quantum experiments, and even to help develop quantum computing, which leverages entanglement. But the deep why and how of entanglement's non-local connection remains a subject of intense debate and research. Does it imply hidden variables we don't yet understand? Or is our concept of local reality fundamentally flawed? Quantum entanglement forces us to confront the deeply counterintuitive nature of the universe at its most fundamental level, a cosmic ballet choreographed by rules we are still struggling to fully comprehend. Now for a question that sounds like it's straight out of science fiction, but is seriously debated by philosophers and some scientists. Could our entire reality, everything we see, feel, and experience, be an elaborate computer simulation? The simulation hypothesis suggests that if it's possible for advanced civilizations to create highly detailed simulations of their ancestors or other realities, and if such civilizations are common, then it's statistically more likely that we are living in one of those simulations rather than in the base reality. Think about the rapid advancement of our own computing power and virtual reality technology. Extrapolate that far enough into the future and creating a universe-scale simulation might not seem so far-fetched for a sufficiently advanced intelligence. This idea is profoundly unsettling and deeply fascinating. How could we ever tell if we're inside a program? Some have proposed looking for glitches in the matrix, tiny inconsistencies in the laws of physics, or perhaps evidence of the underlying computational grid, like a maximum resolution to space-time. AI, being a product of computation itself, offers a unique perspective here. Could AI developers one day create conscious, simulated beings? If so, what does that say about our own potential status? While AI can explore the mathematical frameworks of such simulated universes, it currently has no way to prove or disprove whether our own existence is the product of some cosmic programmer. It's a philosophical rabbit hole that challenges our most basic assumptions about what is real. Chapter 8. The Ultimate Question. Why does the universe exist at all? We've explored mysteries within the universe, but now we confront the most fundamental mystery of all. Why is there a universe in the first place? Why is there something rather than nothing? This isn't just a question about the Big Bang or the initial conditions of the cosmos, it's a question about the very fact of existence. From a purely logical standpoint, nothingness might seem like the simpler, more natural state. Yet here we are in a universe brimming with stars, galaxies, planets, and life, all governed by intricate physical laws. What or who compelled existence out of non-existence? What process initiated the grand cosmic unfolding we observe? This question takes us beyond the realm of empirical science and into the territory of metaphysics and philosophy, though physicists certainly ponder it. Theories like quantum fluctuation, where the universe could have popped into existence from a vacuum state, offer partial explanations. But even then, one must ask, why do those quantum laws exist? Why is there a vacuum state with the potential for such fluctuations? AI can model various cosmological origin scenarios based on the laws of physics as we understand them. It can explore the consequences of different fundamental constants or initial conditions. But the ultimate why, the reason for being itself, transcends computational capability. It's a question that resonates with the deepest parts of our human consciousness, a profound wonder at the sheer improbability of it all. Chapter 9. The Eerie Cosmic Quiet. Where is everybody? Our Milky Way galaxy alone contains hundreds of billions of stars, and many of them are likely to have planets orbiting them. Extrapolate that to the observable universe, with its hundreds of billions of galaxies, and the number of potentially habitable planets becomes staggeringly large, trillions upon trillions. Given these numbers and the age of the universe, it seems statistically probable that life, even intelligent life, should have arisen elsewhere. Yet despite decades of searching, listening with powerful radio telescopes and scanning the skies for any sign of extraterrestrial technology, we've encountered an unnerving, profound silence. This is the heart of the Fermi paradox. If they're out there, where is everybody? There are many proposed solutions to this great silence. Perhaps intelligent life is incredibly rare or self-destructs before it can achieve interstellar travel. Maybe they exist but are deliberately avoiding us, the zoo hypothesis. Or perhaps their communication methods are beyond our current technological comprehension. Or, more chillingly, perhaps there's a great filter, some evolutionary or technological hurdle that is exceedingly difficult for life to overcome, and we don't know if it's behind us or still ahead. AI plays a crucial role in the search for extraterrestrial intelligence, SETI, sifting through vast amounts of radio telescope data for non-random signals. But so far the algorithms have come up empty, leaving us alone, or so it seems, in this vast cosmic ocean. Chapter 10. Infinite Reflections. Do parallel universes exist? And finally, we arrive at one of the most mind-bending and speculative ideas in modern physics, the multiverse. The concept that our universe, everything we can observe, from the closest star to the most distant galaxy, is not the only one. Instead, it might be just one bubble, one island, in an unimaginably vast cosmic ocean of other universes, possibly with different physical laws, different fundamental constants, and perhaps even different dimensions. The idea of multiple parallel universes, each a distinct reality, is both thrilling in its possibilities and profoundly perplexing, challenging our very definition of universe. Imagine infinite versions of you, living out every possible permutation of your life choices in separate realities. The multiverse isn't just a wild fantasy, it emerges as a potential consequence of several mainstream physical theories, including cosmic inflation, which suggests our Big Bang was one of many, and string theory, which postulates extra dimensions and a landscape of possible universes. Some interpretations of quantum mechanics also hint at a branching reality where every quantum measurement creates a new universe. While AI can explore the mathematical consistency of these multiverse models and simulate what such universes might look like if their parameters were different, we currently have no direct, empirical way to prove or disprove their existence. It remains a tantalizing frontier, pushing the limits of what we can know and imagine, a grand cosmic tapestry with potentially infinite threads. Outro: the ever-expanding horizon of wonder. So there you have it, 10 cosmic mysteries that continue to baffle even our most sophisticated artificial intelligence, and indeed, our own human intellect. From the unseen dark matter and dark energy that shape our universe, to the fundamental nature of time and reality itself, these enigmas remind us that we are still explorers on the shores of a vast cosmic ocean of ignorance. The universe, it seems, is far more complex, far more strange, and far more wonderful than any of our current theories or algorithms can fully encompass. Each answer we find seems to unveil a dozen new, more profound questions. This isn't a cause for despair, but rather for excitement and humility. The existence of these deep mysteries fuels our scientific curiosity, drives innovation, and inspires us to keep pushing the boundaries of knowledge. AI will undoubtedly be a powerful partner in this quest, helping us analyze data, simulate complex phenomena, and perhaps even formulate new hypotheses. But the spark of curiosity, the drive to understand why, remains a deeply human endeavor. These cosmic puzzles are not just intellectual exercises, they connect us to the grand narrative of the cosmos, reminding us of our place within its vastness and the incredible journey of discovery that still lies ahead. The deeper we look, the weirder it gets. and AI is just beginning to ask the right questions. Stay curious, and keep exploring the cosmos with us. I'm Dencio Anso. Thank you for joining me on this voyage through the unknown. The universe awaits, full of wonders yet to be revealed, and the quest to understand it is perhaps the most noble adventure of all. Keep looking up, keep questioning, and never lose that sense of awe for the magnificent cosmos we inhabit.